welcome everybody. It's very nice to see you in person after a very long time. All these meetings have been virtual most, so this is a change. My name is Samueli. I'm Chief Computational Scientist at the Office of Advanced Research Computing. And welcome to the exciting topic, exciting presentation on very exciting topic, that's quantum. Let me introduce Professor Jan Palsberg. He's a professor and former department chair of computer science at UCLA. His areas of interest are programming languages, software engineering, and quantum computing. He is the director of UCLA Amazon Science Hub for Humanity and Artificial Intelligence. He is associate editor of ECM Transactions on Quantum Computing. Many more things, including member of the ACM Executive Committee. He has been a recipient of ACM SIG Plan Distinguished Service Award, the Young Instrumentation Inc. Excellence in Teaching Award at UCLA. And the most interesting thing about him is he recently did an executive MBA from Henderson. So he is my senior in that sense. And so without taking much time between you and him, let's welcome.
So quantum computing is getting better, and it's getting better very fast. Today, it's like a toy for small experiments, and I would give it 2 decades until it's ready for scientific computing, and that's going to be 2 very exciting decades. You can just see what's going on at UCLA. We have many quantum people. We have a quantum center. We have a quantum master's degree, and today I want to touch on these points. And what I really want to persuade you is that there's a lot going on. It's a field that's making very fast progress. And so the first point is to make status of the field, and feel free to ask me questions. I have no problems with if I have to go quickly through some material because you ask many questions. I will take any interruption over my own talk. This is a qubit. Quantum computing is this vector. Quantum computing is really a device for making linear algebra go fast. And it computes with unit vectors. So this is a vector of 2 complex numbers. It's a unit vector, and that's 1 qubit. And if you have more than 1 qubit, then you have a longer vector. That's really what it is. And so quantum computing is really just all about that. And the thing that's exciting about quantum computing is that every time you add a qubit, you double the length of the vector. And so already at 50 qubits, you have a state vector of 2 to the 50 complex numbers. That's already so much that most supercomputers have trouble simulating a quantum computer. If you go to 64 qubits, now we are 2 to the 64. So this is like, the number of grains on the chessboard in the old story. If you go to 300 qubits, then we are already at 2 to the 300. That's more than the number of atoms in the known universe. Or maybe, I don't know, maybe the Hubble telescope, but maybe actually now we have the Webb telescope. Maybe there's going to be something, so the number of the known universe is expanding. But for what it's worth, 2 to the 300 is already a very big number. And today, the largest quantum computer I know of is the IBM Osprey, which has 433 qubits. So now it's already above astronomical at this point. It's just a huge number of complex numbers, 2 to the 433 complex numbers in the state vector. And so the whole idea of quantum computing is to use this massive scale to do good things for us. And then I want to touch on why is it linear algebra. And so it turns out John von Neumann way back had this observation that even though in quantum computing we're kind of computing with quantum mechanics, there's an interface to the quantum mechanics that says that quantum computing is really, number 1, computing with a unit vector. Number 2, every step of computation is applying a matrix. And number 3, once we are done, we can sort of go to the vector at the final state and get some partial information about it. And so we can do all of that without knowing, that's important for me, without knowing quantum mechanics or without knowing too much calculus and sort of other bothersome things. So this means that we can take a sort of very nice and high level linear algebra view of quantum computing, which brings us to this picture here. A quantum computer in the future is really going to be an accelerator, where we will use it for what it's good at, and we will not use it for what it's not good at. So it's like we will have our CPUs as usual doing most of the work. And then every once in a while, when the quantum computer is really good at a task, we will load up our bits as qubits. So we have something that looks like a unit vector that the quantum computer can work on. Then the quantum computer will do what it does. And then at the end, this thing of getting some partial information out is usually called measurement. And we get some bits, and then we can go back and use those bits in our classical computation. And so the entire field of quantum algorithms is about finding cases where doing this quantum computing step here is way better than doing it on a classical computer. And way better means faster or scales to much bigger quantities of data than we could do before, or both, either way. And so this means that so we have like the mental model. I'll give like one more little thing about it. So this is a quantum state. So now there's 2 qubits. So it's 2 to the 2. So now we are up to 4 complex numbers. They're not very complex in this case here, but that's what it is. So the mathematicians would write the quantum state like this, and the quantum mechanics people would write the state like this, but it means the same thing. And so we certainly have a vector of length 4. It is a unit vector, as you can compute. And this way of writing it over here, so it says we have a basis vector, which is the one with 1, 0, 0, 0, and this is another basis vector, which is the one with 0, 0, 0, 1. And then we can do a linear combination, or as the quantum computing people like to say, a superposition. They mean the same thing, and then we can write stuff like this. And this state here has another thing to it, which is the quantum computing people like to say that it's entangled. And entangled means that really these 2 positions here, there's 1 position for each of the 2 qubits, and it's again 1 position for each of the 2 qubits. And what we can see is that if we know that one of the 2 qubits is 0, we know immediately that the other one is 0 as well. Or if we know one of them is 1, we know the other qubit is 1 as well. And so this is kind of a famous state. This is one that drove people mad 50 or 70 years ago, because these 2 qubits could be really, really far apart. There could be one on Earth and one on Mars. And then it's like, how can we know something that's so far away without exchanging information? And that's sort of the beauty of entanglement. And in many ways, the way the field of quantum algorithms makes progress is to try to take advantage of entanglement to be able to get a lot done on a large scale. So I want to show you how to produce this state, just to show you that I fired up the Quark simulator. So Quark is written by people at Google. And as it happens, this thing here somehow produces this math that was on the previous page. And so the main point is to say that number one, there's something one can do. So you can see there's time is going from left to right. Here we see something that looks familiar from the first slide. These are 2 vectors. And really what's going on is a tensor product between these 2 to find the initial state. This is a matrix. This funny thing is also a matrix. And then compute, and we end up with the final state. And what this thing is saying over here is that the 0-0 case happens with probability 50%. The 1-1 case happens with probability 50%. And of course, on the previous slide, it talked about 1 divided by square root of 2. By the laws of quantum mechanics, that's the same thing as saying 50%. So this thing here is saying that, yep, we could use the state that I had in mind. And then what the quantum algorithms people sit and do all day is that they build up like bigger and bigger diagrams like this, and then see to that it computes something interesting and does it really fast. So what algorithms are there? So there, of course, we have sort of many quantum algorithms, but the question is, which ones can we actually do and beat classical computers? That's sort of the real question. And so this is the question that makes the quantum algorithms people excited and pretty much drive the complexity people nuts. And so here's like a very computer sciencey diagram, and I'm showing it to give a sense of how little we know. That's really the message of this diagram. So when I write P, that's the computer science people's way of saying problems we can solve fast or in polynomial time in the size of the input. And then NP problems, that's the computer science way of saying the best we can do is just to try all possibilities and hope that we find a good one. And so that's not fast. And then what this BQP is, that's like the computer science way of saying things we can solve on a quantum computer, sort of implicitly implied fast. So with a small quantum program. And so as you can see, we don't really know anything. So it's like, we don't really know where this blob is. And so it's not even, so first of all, it's not really known whether there's anything a quantum computer can do for sure that can beat a classical computer. So we're still kind of working on that. But there are problems where they are like the hardest problems a quantum computer can solve. So we know that physics simulation, very important. The original motivation for the field that Feynman promoted, 40 years ago, that is a very, very good problem for quantum computers. And for the complexity people, it's a good problem because it's the hardest among sort of quantum problems, if you like. So it's the one that has the best chance. NP-complete problems, that's another thing. So of all optimization problems worth anything that people solve classically, they are NP-complete. And so of course, there's a whole field of ways of approximating optimization problems out there on classical computers. And there's a question, so that's like the second big application of quantum, which is, can we do better on a quantum computer? And what this picture is trying to say is, the field believes that the NP-complete problems cannot be solved accurately on a quantum computer. So we're not going to get like a big win from that. But what quantum computers have turned out to be very good at is to solve these, for example, optimization problems approximately. And so that's the same thing we do classically. We have approximation algorithms for solving optimization problems. And it turns out now there's a whole arms race that started in 2014, where the approximation algorithms, both on the classical side and the quantum side, are getting better and better. And every year it seems like somebody's ahead and they're learning from each other. And so very exciting. And it's certainly in industry today, it's quantum computing for the purpose of solving optimization problems that I think is kind of the main use at the moment. And then, of course, there's always a third one, which is Shor's algorithm for solving factorization of integers for the purpose of breaking crypto, which is sort of a much more depressing application, because if they actually can break crypto, then it means that they can intercept my credit card when I pay something on the internet, which is not good. But that's the reason why there's a whole field in math on post-quantum crypto. It's like we got to come up with new crypto that cannot be broken by quantum computers. I just want to say that this space here, you're looking at this space of quantum algorithms, and I'm very happy that people in this room who are thinking about developing more quantum algorithms. This blob here, in some sense, it's getting bigger and bigger. I would say 4 years ago, before the pandemic, there were not that many quantum algorithms. And then it was like the pandemic got people to say, oh yeah, we got to develop some, I don't think there's a relationship. We got to develop some quantum algorithms. And now there's so many more. It's like a very exciting time to go to the internet and say, I wonder if there's a quantum algorithm for my problem over here. And I have just this year, 2023, come across problems that have quantum algorithms. And I'm going to touch on some of them a bit later. But now instead, I want to say something else. So let's look at just quick resources for learning about the field. So I would say, I already showed you this Quark simulator, which is very nice. I remember the first time I fired up that simulator, I had absolutely no idea what was going on, not even a single little bit of what was going on. And now it's some time later, and now I understand much more. And so it really is possible to learn without spending too much time. This book here is Jackie Dari's book. That is actually a very nice book. I teach 2 quantum courses, and when students write to me and said, what should I read before I take your course? I usually say, read this book. So it's a very, what should I say, pedestrian level book. It has 200 pages about quantum computing that ends sort of right around here, and it doesn't go too much into detail about anything, but gives very good information about what it does. And then after that, it has another 150 pages of math you really should know if you want to get into this field. And so it's very convenient to be able to say to students, just flip through those 150 pages. If you know this stuff, then you know you're good. And if you don't know, then the book is there. You can just like read through it and learn or find more resources. Another book is the Qiskit book. So IBM has been out early with providing quantum computing to everybody. And the important bit is that they have the whole Qiskit book online, which is actually a wonderful resource. And now, especially after they hired John Watrous from Waterloo, who is, I think, one of the best lecturers in quantum computing and best writers in terms of clarity and everything, they have really beefed up what they have, just in terms of explaining topic after topic in quantum computing. So I recommend that. And one of the features of that is not just the text, but they have labs for trying out something. And then you got sort of step by step, you know, solve this little bit, and before you know it, you have done something that quite impressive that that you get taken through. I actually use some of those labs as homeworks in my classes, and the students like them. So I recommend those. Maybe I should just say that this thing with teaching quantum computing has been very enriching to me. I have had at this point quite a few professors sit through my classes, and so it's always good fun. So the professors, of course, understand things very fast, and so people have suggested improvements to my lecture notes and asked good questions during the lectures and stuff. And so if anyone is interested, you are absolutely welcome to come to my lectures. So I want to say something else, which is about this thing with simulation. So today, as I will detail later, quantum computers are unreliable, but we can simulate them, or at least we can simulate them up to some size. So I already said that 50 qubits, that's really about as high as we can go, even with the best supercomputers that we have, if we want to simulate anything non-trivial. And in practice, 50, it's like we don't have those resources every day. So in practice, 40 qubits, that's already high. And it's already a couple of years ago that Google announced, at least internally, that they will no longer simulate above 37 qubits because it just takes too many resources. And also, there comes a point where you don't learn anything new about your code after some number of qubits, and they thought 37 is good. But the question is, which simulators can we use if we want to do a little more than this graphical stuff? So there's a web page with somebody's doing a fairly good job of keeping track of all the simulators out there. And so I went there yesterday. So this is one of the quantiki.org web pages. There were 76 simulators, quantum circuit simulators on there that all have status active. There are many more that have status something else, but status active. And so I start to flip through them, and I realized that the one that I actually recommend to my students in my class is still on there and active, which is QSIM from Google. So in my class, it's actually a homework to write a quantum circuit simulator. But I asked them to scale it to 16 qubits, which is like much more. It's a huge difference between 2 to the 16 and 2 to the 40, right? So writing something that doesn't really scale so much is fine. One can do that in not too much time. But making it scale, that's really where the value of some of these simulators one can get from outside. That's where it is. And another thing is, if one wants to get the impression of running on a quantum computer, then people will build in noise. So they will build in that is not accurate, that there are errors in there. And all of this, of course, takes time if you want to simulate it. There are many different ones, but I must say I like QSIM. So just to give you a sense of 2 to the 40 in my mind, so we know it's 2 to the 40 complex numbers, but of course, if we just say 2 to the 40, that already sounds like a terabyte, right? It's kilo, mega, giga, tera, right? It's just to keep track of the state, that's already a terabyte, and we want to do many operations, so it's a lot of bookkeeping, a lot of space is getting used. Okay, so that was sort of status of the field. So now I want to talk about this thing with this, my point that I think it'll be a couple of decades before quantum computing is ready for scientific computing. And so, so to me, when thinking about quantum computing, it's kind of thinking about MATLAB. I'm sorry, I'm thinking about scientific, and now I'm switching to scientific computing. I'm thinking MATLAB. So, so I want to just to say a thing. So I'm in computer science, right? And we have a conference that's approximately every 15 years of history of programming languages. And last time, MATLAB got in there. So there's a whole paper written by Cleve Moeller, who invented MATLAB, on the history of MATLAB. And I was actually his shepherd. So I got to talk a fair bit with Cleve Moeller a few years ago. And it's really exciting to hear about the early days from the 70s, from the early 70s when they invented this. And I just want to sort of bring home the point that MATLAB is short for matrix lab, right? It's really matrix. So it's like you can carve out a bunch of scientific computing. It's really about matrices, and it's great. So we have some scientific computing that's really applied linear algebra, and quantum computing, which is applied linear algebra. And there really ought to be a close connection there, and there is. So when I look at some of these scientific computing projects at UCLA, what I see is that first the professor spends a week, writes a MATLAB code, gives it to the graduate student spends half a year writing the same thing in C++, so it goes much faster. And then that person hands it over to a postdoc who spends another half year writing like the CUDA version or something that will run blazingly fast on a parallel computer, right? So the question is, how is that going to go if we give this to a quantum computer instead? And I'm going to go into this a little bit. So just to give some examples, so I can make this concrete. So here we have some functions that are supported by MATLAB. PCA does principal component analysis, which is this thing that you just want the eigenvectors for the largest eigenvalues. Then we have non-negative matrix factorization, which is in a way akin to principal component analysis. We just want our matrix broken up as a product of two matrices, and we insist that those two matrices have only non-negative elements. And then, of course, the fast Fourier transform. Very important because to relate to the quantum world, because when we look at Shor's algorithm, the intellectual content inside of Shor's algorithm is that we can find the order of a group exponentially faster than we can on a classical computer. And the reason we can do that is fast Fourier transform, or rather, we can do quantum Fourier transform exponentially faster than the fast Fourier transform. I think the fast Fourier transform is like n log n in the size of your data, and the quantum Fourier transform is exponentially faster than that. So, so in a way, there are quantum equivalents of these, and they, as far as I read those algorithms, in all three cases, are exponentially faster on a quantum computer than classically. So there should be huge potential here for doing something. So I want to talk about what that could look like a little bit, and what we could get out of switching to quantum. So here is a couple of papers from so my main collaborator is the last author, Sriyam Thankaraman, he has a joint appointment in computer science, computational medicine, and human genetics. And so he's working on these big DNA data sets, and he's trying to find out stuff. And so what he does is that he brings in DNA from many individuals and then try to find out something. And so this paper here, C2020, what he does is that he tries to find out if there's signs of natural selection in the data. So we can see if there's natural selection among the genes there. And how does he do that? He runs principal component analysis, which pretty much means that it seems like the entire computational content is one line in MATLAB, right? Because it's there. Of course, this is not really true. This is why it's a scalable probabilistic PCA. So his data set is a big one. We'll get back to that. So you cannot just run the MATLAB version. Second paper, so here they are going after finding out if you have a higher chance of inheriting a disease, that one can see that there are people with the same genetic makeup tend to get this disease, and then maybe you're going to get it too. And the way they do that is that they do, as it happens, non-negative matrix factorization. So again, it seems like the entire computational content of this paper is one line in MATLAB. That's not exactly true, because the data set that they use is what I know as the UK Biobank data set. So, so there's about 500,000 individuals in this data set, and they know a lot about those people, and it's all there, very nicely readable. And sort of for the purpose of thinking about this, let's just say that we look at 500,000 genetic variants. So it's like for 500,000 SNPs, we get some information about what's different between you and your parent. And so that's a lot of data. That's like 500,000 by 500,000. So they organize this data into a matrix. Every entry is a 0, a 1, or a 2, which really have to do with, is there any difference between you and your father, you and your mother? Either there's 0 difference, 1 difference, or 2 difference, right? That's what it is. And so you get a matrix that doesn't look too different from this, except that it's 500,000 by 500,000. And then it's like, okay, so when they run principal component analysis on this data, it's like half an hour, maybe not too bad. When they run non-negative matrix factorization, that's a couple of days, and they're not running on a laptop, right? They're kind of quite serious about it. So, so it's like, okay, so today, something like 30 million people have had their DNA sequenced. And at least we can dream that one day it's all 8 billion of us have had our DNA sequenced. And then we can say, oh, so can we now take the second paper there that today runs in 2 days for 500,000 people and just scale it up 4 orders of magnitude? And it's like, no, this is not going to happen. So quantum would have potential to scale up here, because we would be able to go exponentially faster for the main algorithm. So I want to take a moment to say that I said in the first sentence that quantum works on a unit vector. None of this looks like a unit vector, so one has to do something. Of course, one can always scale, right? So that's fine. But there is one more thing in quantum, which I have been very quiet about, but at some point I have to say, it's all about unitary matrices. So going all the way back to von Neumann's observation about the interface to quantum mechanics, it's all about unitary matrices, which in this setting here, we could just think of as that all the columns have to be orthogonal unit vectors. And then we can say this one is definitely not orthogonal unit vectors. So that's not good. So this matrix is like a bad fit for quantum computing. But we can make it a good fit by doing what's normally called a block encoding. We take the whole thing, we put it here, and then we just fill in nice things to make it twice as big dimensions. And now we can make it unitary, and then it's ready for quantum. Okay, we have to scale it too, right? Scale it and then block encoding, and it'll work great. And then one can say, okay, so we just started with 500,000 by 500,000, and now I'm actually effectively talking about 1,000,000 by 1,000,000. And isn't that like maybe asking a lot? But in quantum computing, it's not, because in quantum computing, that's one more qubit, because we double every time we add a qubit. So it's just like not an overhead at all. And so you can see scaling 4 orders of magnitude from 500,000 to 8 billion. That's like 14 qubits or something, right? It's like if we could get this to work for 500,000, we can definitely scale it to 8 billion. It's not a problem. So so that's kind of one dream that one could have, that as we get more and more data, we will be able to find more and more information that eventually will help the whole health endeavor of healing the sick. So let me just stop there with my sort of endeavor into scientific computing and say there's really hope for doing more with quantum computing, and then say something about what are the breakthroughs that we need to get to this. So I want to focus on at least 3 breakthroughs that we need for sure, and I think there are more. So we need more qubits, we need more reliable qubits, and we need those qubits to last longer than they do today. And so I'm going to like go into each of those 3 pieces. On a web page, I think on Wikipedia, there's a very nice listing of all the quantum computers that we have today. Some of them may exist in more than one copy, but there are not very many copies for quantum computers. So what I did was that I plotted them. The first quantum computer really sort of that was worth anything came out in 2016. And then number of qubits is on the y-axis. And you can see that this really is this one that I mentioned, IBM Osprey, is this one up there. And there's one from China, which is there. And so those are very good. But then there are also many other ones. And the reason why there's a lot of stuff going on down here between 0 and 100 is that people are both trying to show that they can scale the number of qubits, and they're trying to make the qubits more reliable, the operations on the qubits more reliable. And so it means that there's a need both for scaling and for working on reliability. And that's usually 2 ends of the spectrum. And then the red line, that's just doing linear regression on this data. And what this linear regression says is that if we ignore all the details, that we are adding a qubit every month on average, which that's kind of like Moore's law for quantum computing. That Moore's law for classical computing says that we can pack twice as many transistors into a particular space every 2 years or so. It's been going for many years. Here we are doubling the size of the state vector every month. And I have computed that if we are, so that we should sort of ask how many qubits do we need? So people have high hopes, right? So we can look at Google's, they have a roadmap for quantum computing. The roadmap talks about going to 1 million qubits, actually. So they have this sort of whole, there's a beautiful animation online you can find about how we are walking up the mountain, and at the top of the mountain is 1 million qubits. And it's like, okay, so why are they talking about 1 million qubits? And the reason is the second bit, which is the reliability. So today, there are techniques theoretically for error correction, just like we have error correction in classical computing. And at the moment, those techniques call for that you need 1,000 physical qubits to create one perfect logical mathematical qubit. So every time you see 1,000 qubits, it would be 999 is this there to support the last one. And so there's only one of them doing anything. And so this means that 1 million qubits, if we can ever build such a computer, which Google's roadmap says we will do by 2029, then we can support 1,000 real logical qubits. And so then one can say, okay, so is 1,000 qubits going to be any good? And so actually, in this whole DNA story I gave you, I actually think 70 qubits may be enough to scale to maybe even the whole world. Other application, we need many more so of course, the goal is we want to beat classical computers, right? So the real cutoff is how many qubits do we need to beat classical computers? I keep asking around every time I meet somebody, and the answers I get are anywhere between 500-700 to 3,000 to 6,000 qubits for different applications. You know, there are more and more applications. I think that this DNA may either maybe I'm doing an underestimate, or maybe it's like a sweet spot of something. I don't know what it is, but 1 million qubits is actually has a very good chance of being good. So then one can say, oh, that was Google says 2029. That's great. So maybe my prediction of 2 decades is too pessimistic. But I want to bring up another point, which is this number here. So that is actually a dream more than it's reality. So here I'm talking about the reliability of a single operation on a qubit. So every operation by John von Neumann's observation is applying one matrix, and that operation succeeds with some percentage that's not as high as this today. So depending on what way you build qubits, and nowadays there are always things you can use ion trap qubits and superconducting qubits, and then there's a whole bunch of silicon qubits and neutral atoms, and there are other ones coming up. They all have sort of strengths and weaknesses in how reliable can we make them today, how easy is it to scale them to many qubits working together. And none of them have reliability this number, as far as I read the literature. This is going to be a big day when that number comes up. Maybe this year. I would actually be optimistic that it might happen this year, but we haven't gotten there yet. And so what it means, of course, is that if we are executing lots and lots of operations, even a reliability of this is very quickly going to mean that the overall reliability is going to be like nothing. We would be better off flipping a coin. And so that's why the reason why here we are at the core of the reason why companies are not like rushing to just build 1,000 qubit quantum computer, because we wouldn't be able to use it for anything. It would just be there to show that we can run the computation, but the result wouldn't mean anything. So reliability is very important. So we have like 2 groups of people working. There are those who try to build more reliable qubits, and those who try to put qubits close together to make bigger quantum computers. And I think that there's lots of hope here. There are many more people working in the field than there were even 5 years ago. So I think there are many new ideas coming up. So we're getting new ideas for algorithms, new ideas for error correction, better hardware, and the field is changing. 15 years ago, it was surely ion trap qubits that was like the game in town. Today, when we look at the IBM's quantum computers, Google's quantum computers, Intel, at least the one I know, Rigetti, which is a company in San Francisco, they are all superconducting qubits that they use. And then, as it happens, now there's this whole movement of building neutral atom qubits, which seems to be very promising. And then we should not forget that we have HRL out here in Malibu, and Jason Petter who moved to UCLA not long ago, who's building these silicon-based qubits. And all of these different technologies have different advantages and disadvantages, and people are, of course, working on making it all better. It's very hard to say what will emerge as the best among these, and maybe there won't even be a single best. So it's a very, very exciting time also on the hardware side. And then there's the third thing. So that was scale, many qubits, very reliable qubits. But there's one more thing. This picture is actually from Faroe Islands, which I'm from Denmark. So Faroe Islands is under Denmark. I want to show this. This is a soccer pitch. And what I want to illustrate here is that in quantum mechanics, all these computers, they work at very, very low temperature. So, okay, I'm not saying that Faroe Islands is very close to the absolute sort of freezing point, but quantum computers are. It's just quite cold up there. They still play soccer, and they're actually quite good at it. But just like with a quantum computer, that at some point the quantumness will go away, and then that's it. You cannot compute anymore. Here it's like if the ball goes out of the pitch, then that's probably it for the game. You're not getting the ball back very easily. And so another dimension that people are working on is to get the sort of the period you can do quantum to be as long as possible, so we can actually do these computations that we want to do. So so one of my estimates there is saying that if we want to do this non-negative matrix factorization on this what is that, 500,000 people in this UK biobank data set, we probably need something like 50 qubits, but we also need something like 70,000 operations, 70,000 matrix operations, right? And that would just not be possible on today's quantum computers. They would run out of steam. They would run into decoherence too quickly. So that there's something real there that has to be done. And so I think that when I say 2 decades, it has a lot to do with, we will be able to scale to a lot of qubits soon, but I don't think we're going to get to reliability that soon. So for the quantum computers to really for all this error correction or reliability, whatever it is, I think we need more time. Anyway, this is what I think. So I think I'll stop talking about the scientific computing angle on this. And I just want to say something at the end about good reasons for joining the field, or at least saying something about why there's a lot going on at UCLA, and you will be able to connect very easily. So there's so much. So we have a center, we have people, we have all kinds of things, and there's money out there. So as you know, 2018, the president signed the National Quantum Initiative that allocated $1.2 billion to quantum research. And then we see all kinds of call for proposals coming through. So I just list one from the Department of Energy, one from DARPA, one from NSF, and this stuff is just coming through all the time, tens of millions of dollars at a time, usually. And so, so I would say if we look at the size of the field and the amount of money that has been allocated to it, it's actually a very good spot to be in. You know, some fields have a lot of competition for money. This one, not so much, I would say, at the moment. So just to let you know. And that there's a lot of people here at UCLA that one can partner with for some of the call for proposal that require partnering. Let me show you a picture here. So here's a picture of, this is a pre-pandemic picture of some of you here may be in the picture, not sure. So so this is like people in the center. So we have Mark sitting here in the middle, who is our executive director. Kang Wang from Electrical and Computer Engineering is the director, and so they are both in the picture, and there are many more in the center. So it seems like both engineering and physics and chemistry and math and material science and more departments, they keep hiring quantum professors. So there's just a lot going on, and certainly more students that are in this this picture here. And there's a web page somewhere. So I think the web page is even behind listing all the people. There was a time where it was my ambition to know the names of all the professors in the center. And I must say, I cannot keep up anymore. And of course, if you want to know some of the names of people who build qubits, so Wes Campbell and Eric Hudson, they build ion trap qubits. Now we got David Librand joined recently, also built ion trap qubits. Jason Petter, I mentioned already, who builds these silicon-based qubits. There's just a lot going on. And that's only talking about quantum computing. Then there's also quantum sensing and quantum optics. And there's a lot going on in these areas. And actually today, I would say that quantum sensing in the near term, which is like this decade, is more promising for short-term wins than quantum computing even is. Quantum computing is, for me, is like a next decade thing, as I've been trying to say. Some of these people then have started a master's degree, which I also will mention. So here's like the layout of the degree. So we have 24 people in the first cohort that started last fall. The graduation party is on Wednesday, I've heard. And there's a lot going on in Los Angeles. So many of those 24 and me and Mark and other people were down drinking in the arts district with people from Google and Caltech and Amazon, AWS and Caltech and USC and HRL, and there were people from Atom Computing at Berkeley who came down, and more. There's just like, there's a whole movement in Los Angeles going. And So the 24 students take these classes, and the thing that's the hallmark of this is they take labs all the time. So for a whole year, they go and work with building qubits or working with quantum sensing or working with quantum optics. And so really learning the lab side of this. And the reason this is important is that this is what industry needs today. They need people who can work at what I think of as the level of just very near the interface of hardware and software. And so we educate people that we think industry will be interested in. And then as it happens, they take my class in quantum programming and another class I have in quantum algorithms. That's like a little sequence. So that class is populated with mostly engineering, mostly computer science students, but then there are all these master students as well. And there are always some Ph.D. students from physics and math and chemistry in there too. This has actually been a fun experience so far. It's very enriching when you have students of so many kinds. And the saddest thing about teaching these courses is I simply do not have enough capacity, because I have the students run on quantum computers, and there's really only so much one can expect from freely available quantum computers. But one year we got access to run on the Google Sycamore, which is the best quantum computer they had at the time, but that we could only do 1 quarter. And then one year we got access to Righetti's best quantum computer, but that only works for 1 quarter. So most of the quarters we run on a freely accessible IBM computer. And then at that point, we have to restrict access. And that also means how many students. So I normally have about 80 students in the class, but I have like 100 who cannot get in. And so that's the sad part about that. So anyways, I think I will stop here. So it's a field that's making a lot of progress. There's a lot of people coming in. There's a lot of improvement every year, both in number of algorithms and the number of qubits we have, in the reliability of the qubits, certainly in coherence time, and generally sort of what people imagine that we can do with this stuff. And I think we are still in the early stages. We are still in like the radio tube, whatever era of computing. So it's like early 50s or something of classical computing. And there's so much more. And so I would say for you, there's so many good videos on YouTube. I watch them. I learn a lot from watching videos on YouTube. I recommended a book already that you can flip through that I think is very, very nice for a first book. And then, of course, we have plenty of quantum people here at UCLA. Just find one of us and talk. Thank you. Any questions?
You mentioned the 99.99%, right? The fidelity. Why do you think could be optimistic to get it this year, and from which area, which kind of side of the spectrum?
I'm piecing together information from different sides, right? So I'll just give you like a quick rapid fire bunch of data points, and then in my mind it sounds good. So in Eric Huston's lab, they have fidelity of just like firing up a qubit and measuring it at 99.7% accuracy. So that's very close, but that's also very basic. Then I talked to somebody at Amazon AWS out in Pasadena the other night, who they're building a particular kind of qubits, and they were definitely well better than 99.9. And I was asking him, when do you get to 99.99, right? I asked everybody, and he sounded like, maybe this year. So it's like, okay. And then on the neutral atom side, it seems like the whole advantage of neutral atoms is that reliability is much easier to get. And so I may be misreading the papers, but I am very optimistic there that they are on a curve. And then the last point is, I asked the Google people about how's their reliability improving for superconducting qubits, and they said it's a linear improvement over time. And so if that linear curve keeps going, I think they will hit 99.99 quite soon. Actually, they're already better than 99.9 for single qubit operations. Yeah.
I want to ask about quantum supremacy. What's your favorite example that you can explain to us that the quantum computer has already done? It's better than a classical computer.
There are no such examples. That's easy. I think there will not be any such examples for 10 years for sure. 10 years for sure.
If you read about people arguing that this one sort of big bizarre kind of thing was actually done better.
No, yeah, but that's okay. So, but it has to be interesting examples. If it's something you carefully ask, something that I can explain, right? So something like sorting, or right, something that we immediately can grab onto, say, I understand this, or principal component analysis. but those examples don't exist today. So, but if we want to go into something that cannot be explained easily, really what's going on today when people talk about quantum, any kind of quantum advantage over classical is that they take a random circuit and then they show that a quantum computer can execute it faster and get to something that's at least is recognizably not random and do it much faster than a classical computer would. So a classical computer could simulate it and get the best possible answer in like whatever time. And then the quantum computer can do it faster, but the result will be almost random, but not far. So that's the level of advantage we are today. And people have very hard time making progress beyond that point. So I saw a talk by the chief architect of Google's quantum computer just a few weeks ago. And he talked about that it used to be that they were like 2% away from random. And after 3 years of hard work, they're now 3% away from random. It's like, okay. So no, there is no real case for quantum supremacy.
When you mentioned the computation sort of running out of steam on qubits, is that because of the amount of energy required for the cryogenic state, or you need to get the cryogenic state lower? What's the reason?
I cannot answer this very well, but it's roughly what you say, that the quantum computing is happening at something less than 0.1 Kelvin. And it's a lot of energy that goes into getting it there. The Google people told me that it cost them about $1,000 an hour to keep it in the air. And at some point, it's like the world interferes. It's like that you get the interaction with the outside world, and then at that point, everything falls apart. But the real answer to your question, I actually don't know what it is, but there are people at UCLA who know this very well. Yeah.
In the first slide, you mentioned about the accelerator as I'm trying to envision like if it is so hard to build a quantum computer, how it will be integrated with that.
It'll be a data center thing. We will have a room at UCLA, or we will have access to a room at USC or some place where the quantum computer is and nicely cooled and everything. And then we will access it the way we access every other cloud resource. Yeah, it will be a cloud thing. I actually think that part is not hard. It is like people have already kind of solved this, so this will work.
I actually work on population structure with UK Biobank.
Very good.
Yeah, so thank you for answering lots of questions.
Oh, you one of the co-authors of these?
No,
okay, all right.
I wrote another paper in the journal.
Sure.
Yeah. So is there active work on quantum computing for that particular problem?
Yeah.
At this point?
Yeah. I'm also working on it. We are working on it. Absolutely. So you should talk to us.
Yeah.
We'll be happy to. Yes. Other questions?
So, well, thank you for the talk. I went to the Winter Quantum.
Oh yeah,
School.
that was a good one.
And it was a very good one. Yeah. So it's a very exciting field, but my personal question for you is that I see a lot of dissonance between what the industry is saying with quantum computing and what here, from a research perspective, we know it's true, right?
Right.
So I went to a talk a couple of months ago with a consulting company that I will not name, but they were already arguing that quantum supremacy existed. Which is, I think, a very questionable thing.
Yeah, that's a very questionable.
Yeah. So, do you have any thoughts on how research community that we want to form here at UCLA can battle this? Because a possible outcome that I see from this dissonance is what media outlets like to call like a winter, quantum winter or something like that. Like what industry or the model comes from loses faith because it says, okay, you said it was ready today, and now you say it might not be ready in 10 days.
I went to a talk by at Google by the guy who runs the Google Quantum Project, and he said that he believes we have until 2030, maybe 2035, until in his case Google, or in our case the federal government, runs out of patience. So I think we have some time, but we do not have infinite time. And so I think it's a little bit like. So here's like a little bit more poetic version of the same thing. So there was the 1957, the Sputnik moment, and the US was like, oh, we have to do something. And then they come up with DARPA and the moon plan, And in '69, there was the moon landing, right? So what happened in the quantum space was 2016, the Chinese sent a qubit from a satellite to Earth, and the US was like, oh, and then they started the whole National Quantum Initiative, and now there's a lot of quantum research and so on. And what we're waiting for is a kind of a moon landing for quantum, where there's something big, tangible. Actually, maybe I should just say we need a ChatGPT moment for quantum. Right? It's something where everybody sits right up and says, "Oh, this is like fantastic, something new." Right? That moment we can all hope will happen this decade, but I'm not so sure. And so that's one of the reasons I became interested in this whole DNA project, because it seems to me that that's a chance for doing something with less than 100 perfect qubits, which may mean that we will need less than 100,000 physical qubits to do something, which will come way sooner than 1 million qubits, I think. So anyway, so this it's of interest to everybody where is an application that could give us this moon landing thing. But back to the question about what the consulting companies and press and so on says, this can be like disregarded for the most part. It's very early days. It's very easy to be optimistic, but the optimistic is based on dreams. It's not based on anything we have today.
So what kind of reliability do you think you would see with a logical qubit that's based on 1,000 physical qubits?
Well, at that point, I think that it will be so good that we can think of it as being perfect. It will not be
the error
completely
ratio
true.
doesn't exceed what we see today on a per operation basis, or
There's always this thing. I'm just thinking, I'm looking at this computer here, right? The error rate is probably like 1 error every year after error correction, right? We may not get to that quite for quantum computing, but something like quite high. So I want to make a point. So there's in error correction, and certainly in quantum error correction, there's a precious theorem called the threshold theorem, which says that if your error of each qubit, in this case, is below the threshold, so the reliability is above a certain threshold, then at that point we will be able to stack error correction on top of error correction and get to whatever epsilon you want. And so I have made another point out asking everybody I meet, what do you think the threshold is? And I would say that nowadays the threshold people give is usually not too different from either 1% or 0.1%, which means we are already there. So so it means that if one wants to take a really optimistic view of this, then give me 1 million qubits today and let's experiment with the like error correction on top of error correction that we have, and we may actually make it work. That I actually don't completely really believe this story, but I think we may not be as far away as it sounds. In the end, I think what the world will be like in 2030 is that we will have more reliable qubits, but they will not be like tons of nines. It will be just better than it is today. But the error correction techniques will also have become better, which means that we won't have to stack too many error corrections on top of error corrections. And so it means that we will be much, much closer at that point to something that works. Other questions?
What types of problems would you think that we would get quantum supremacy for first? Like 10 years down the line, 20 years down the line, where do you expect?
So what I really think, other than, of course, I know we talk about DNA all day, but what I really think is that for physics simulation, for simulation of quantum physics, I think that is, so I already mentioned that this was the original motivation of the field, and to this day, I think this is where there's most hope. The reason is that, so now we're getting into another thing that many things get glanced over, but the thing is that physics simulation, of course, because it's simulating physics, also can take advantage of some of the things that's true about physics, which is local interaction. And so a quantum computer, in the end, is a physical thing. And it's easier to program stuff where that local interaction, and you don't have to think about moving stuff around that are far apart. And so I actually think that physics simulation has a lot of hope, because you're just trying to simulate, whatever it is, something that already is just local interactions, and which now becomes local computations. And so people are excited about physics simulation because they want to discover new drugs. And so they want to simulate particularly quantum chemistry. Okay, so a particular branch of physics. I think that this is, if there's going to be a breakthrough this decade, that's where it will come from.
Yeah, I have a general question about the, acting on matrices, basically. So when you think of this as a linear algebra problem and there's these algorithms for doing things quickly, but you have to prepare the state vector, right? And so you have to load data into in some way, right? And so the short thing is a particularly nice example of how you can get around that, right? Because you can prepare the initial input state very efficiently, right? But if you're just loading arbitrary data into a state vector, then you have a real bottleneck there.
Yes.
So do you have comments on?
Yeah, so that's another, so we swept so many things under the carpet today. That's another one. So let me start in an even more general point. So people are excited about quantum machine learning. The reason is that there's a whole lot of machine learning which is applied linear algebra. Quantum computing is applied linear algebra, so the two ought to meet, right? The problem is that machine learning is inherently about a lot of data. And if that data is going to be loaded up onto the quantum computer, as you said, it's going to be loaded up as a giant unit vector. And that is a problem. So it means that we got to get that unit vector from somewhere. And today, when I ask the people who actually know what they're talking about with state preparation, they say, oh, you give me QRAM. So QRAM is like quantum random access memory, where we can then sort of get all our data organized correctly. The problem is that we don't have QRAM. QRAM is just a dream. And I want to mention, so I teach these quantum classes every year, and every year I put the people in groups, and they have to come up with a group name. And the best group name so far is QRAM is a lie. And so until we have QRAM, the whole idea of quantum machine learning is essentially just a dream. And in general, for very large data sets, it is absolutely just a dream. And this applies to even to the DNA project, where up to probably for the 500,000 people, we will be able to get away with just using a classical computer and then actually arrange a state vector with maybe 50 qubits or something. But that's for the same reason as simulation is more or less goes to 50 qubits. At some point, we just run out of classical resources to do what we want to do. After 50 qubits, I think, no. So what is 50 qubits? That's 1,000 terabytes, right? That's a petabyte, something like that. That's about as much as I think there's any hope for doing in a pedestrian way without having QRAM. And we may never have QRAM. So it's like, yeah. QRAM, that's that. If I was going to list the breakthrough number 4, that would be QRAM. We absolutely need QRAM.
At what point, I mean, quantum computing has potentially some negative externalities, right? Vis-a-vis cryptography and things like that. And at what point, how many qubits before we start getting to some potentially worrisome uses in, for example, cryptography?
Yeah. So the good news is that of all these different algorithms that I mentioned, we talked about today, Shor's algorithm is like way out there in terms of how many qubits it needs. So that one is neither first, second, or third in what we'll get to. The problem is that people have already started to store our encrypted emails and our encrypted telecommunications, and they're just waiting for quantum computers to be fast enough so they can decrypt them. And so in a sense, it's already too late. It's just like there's a delay in reading our stuff. The day they announced they have a very big quantum computer, I really hope that we can switch to a different way of encryption. But those externalities are not there yet. So it's like those things where quantum computing can do stuff we kind of don't want, that they happen to be the most resource intensive. So not so bad yet.
So if I think about the history of different technologies, I think about airplanes, telephone, telegraph, all radio, et cetera, all of them seem to have been done by either small groups or individuals until they got some success, and then lots of people sort of jumped in, right? And this seems different in that there's an enormous amount of very smart people that came to career with governments putting money into it, companies putting money into it, without any success, all working towards one particular thing. The closest thing I can think of, here's the question here, is something like fusion power, with lots and lots of effort to try to do something. So my question is, why is the community generally in some sense, so convinced that this dream is going to bear fruition that justifies all this investment as opposed to something that simply may never happen.
I think okay. So first of all, I want to hedge and say that I actually don't know anyone who's very convinced that this will all work. I think it's more like any research project, we're hoping that it will work, but it's I don't think that there's any sort of guaranteed success here. The second thing is that the problem is that if it succeeds, it will be so disruptive that it's much better to have it than to not have it. And so this is why we have the whole like quantum race between the US, China, Europe. This is why companies absolutely want to get there first. And so now I think it was said in the introduction that I'm sort of more than a little bit connected to Amazon. And for Amazon, the reason they're interested in this, I think the way I see it is the way Amazon makes money is on Amazon Web Services, right? That's by far the biggest profit maker they have. And if there's one thing that threatens web services the way we know it today, it would be quantum computing, because you would be able to do things much faster. And then somebody would be able to say, oh, I don't want to use AWS anymore, I'll use this much faster thing over there. And so people want to get there first.
So the model is more like the atomic bomb, right? That people feel like they've got to make that.
Yes.
Because someone else might.
Yes. And with the atomic bomb, that was not guaranteed either, right? But people thought we gotta have it, so we'll just do what we can. They succeeded very fast, though. This quantum will take longer. If it's going to succeed, it will take longer.
Yes, thank you. I'm curious because you mentioned there are some things that quantum algorithms, quantum computers just don't have an advantage of. I've heard about hybrid classical and quantum approaches. Could you comment a little bit about that? Is that a practical way that we solve real scientific problems, or is it just a bad thing?
So what my picture at the beginning was intended to show is that in a way all quantum computing is hybrid. In the way that the main computing, like our operating system and web browser and email and stuff, that'll all be classical still. And then there'll be these subroutines for which quantum is very good, and the classical computer will then use the quantum computer as a subroutine and get an answer back. So in that sense, all quantum computing is hybrid, but it's even more hybrid than that, in that if we look further into what quantum algorithms are doing, even at that level, they're going back and forth between classical and quantum a lot. And so the future is hybrid in that sense. If you're going to get quantum to work, it will be a hybrid. It will be a hybrid way. And as always, when you need different computing paradigms to work together, now suddenly it becomes interesting to think about how do we write our programs, how do we make this work, and all this. So lots of work for the software engineering people there.
Will the bottleneck be the data transfer from computer to computer?
It will absolutely be a data transfer, a bottleneck with a data transfer, and so we have seen how the classical people have been addressing this for heterogeneous computing the last decade. With first we got chips where there would be a shared memory between a CPU and a GPU, and then they got something where I think they can do it with a CPU and an FPGA. Just have the memory right there, so it's on the same bus. And I don't think that this can happen for quantum computing. So I think that with the knowledge I have today, I would say yes, there's going to be a bottleneck that's going to be an actual problem. Papers tend to just sweep this under the carpet too. So maybe that's another breakthrough we need to somehow get over the data transfer bottleneck. Thank you.
So maybe a follow-up of the question he asked. So with this quantum machine learning topic, personally, I'm very skeptical as well. But you mentioned one of the biggest bottlenecks or problems with this quantum realm, but I think of something maybe even more basic, that it's quantum computing is in practice a linear operation, right? And most of the machine learning that we see today that is disruptive is full of non-linearity. Do you have any thoughts maybe that can be tackled, or maybe it cannot be tackled?
I'm sorry, I know too little to really give an insightful answer about that. But as always, what happens with quantum computing is that even for sort of nonlinear stuff, then they look for a linear approximation of it. And so some of the optimism for quantum machine learning comes from that, from linear approximations of whatever it is. So, but I like personally think that there's whole areas of machine learning that probably is not very amenable to quantum computing, but it seems like I keep getting proved wrong about this, so I'm actually not sure. What I do in my class, actually, in my second class about quantum algorithms is I simply ask the students to write an essay about quantum machine learning, the state of quantum machine learning. Then I don't have to teach them anything, so I'm not wrong about it. Any more questions?
Let's thank. And feel free to take some of the snacks. They will be like here. Thank you.
I learned a lot. But so, is it always, you know, when we talk about the quantum letter or whatever, so this mostly like economics, psychology, politics, or is it mostly like if it's like what they had in bullshit for failure?
The more I take it, the more I.
The expected time to build progress is just super far in the future, and so these are not smart investments, or is it just like people are patient?
Of course, people are patient, but I think it's not. I think the problem is that there are enough breakthroughs that we need that each one is doing how long. And then once we don't even know if they should multiply them.
Right, but it is, yeah, we would learn something about what that hazard function looks like by experiencing the next 10 years.
Yeah, that is the problem.
That's interesting.
So it makes it very hard. I talked to my old friend, vice provost, and recently reduces to invest in said it's too expensive, too uncertain. It's like you're not going to
It's a totally interesting thing because, you know, in all these kinds of things, especially if you think about it like from the point of view that I often think of things, you know, like you could do what Berkeley just did, which is invest a huge amount of money in college yesterday, as far as I can tell. I mean, better than a college, than the $200 million investment in 100 years ago.
Yes.
Which we also did 50 years ago. But you'd rather make a $200 million investment. But then you gotta have a pretty good idea. This is really like, this really is like, I mean, maybe the future now is not an adequate. It's like the 1960 that could have been in 10 years, or it could have been 50 years, or it could have been never.
Yeah, absolutely.
And every year that goes by, the more likely it is that it's never gets a little bigger, but also not.
So but I also want to think of this in a way, just like when there's a war, we develop all kind of new technology that will benefit us from the war. And more than spawned off lots of different technology. I hope that the same will be true here, that it's spawned off lots of things. We actually want to have.
When you carve up a massive system integration problem into a lot of little pieces, so you learn stuff about those little pieces that have much broader application. You know, and that's, yeah, you could figure out.
Well, in this case, yeah, I already mentioned something where there's an arms race and algorithm or something in particular. Classical people already sound better because it's like, oh, now we're
or maybe you see different ways of doing a problem. Well, that isn't that quantum solution, which is very accessible from that perspective, actually has application that is not obvious.
So there are examples of this already, particularly in quantum machine learning, where the very short version is that 54 years ago, there was like a list of 50 problems in quantum machine learning that people said, look, we are better and classical in all of these. And then there was actually an undergraduate student at UC Austin, he dismantled 12 of them and taking these ideas, carrying them over.
What's better about this is not that it's quantum.
It's just better. Because when you take the content, carry it over to classical, and now that's much better.
You got to prove something about quantum, and prove something about the algorithm.
Exactly. Very good.
And then this is John's question, but I would just say, so sort of like when these computers actually get built, like how general purpose, when you teach a course on a programming, is that like something you do with soldering irons, or is that something that Or is that like?
It's not so super slim. So I think that this is where.
So like when you put that room, there's actually in that rack, like or whatever it is, there's a box that does, you know, non-negative, matrix factorization, or there's a box that does.
Yeah, that's what it's gonna do.
It's not a program that you're gonna run on this.
Yeah, right. I think that that's exactly what it's going to be. That once you've got so much effort getting a particular way to do something, then you keep it and you box it up.
Certainly does this, that I should think of that in a very literal physical sense, it's like this is.
Yeah, of course, the way we model it, it is programmable. It still looks like it's programmable in computers. But
Well, when we model it, yes.
but in practice, I think that it will be much more static. It'll be much more like this sort of specialized hardware. In practice,
Very good at doing this game.
This exactly. In practice, yes. We because of error. That's the thing.
Yeah.
So.
My name is Jason. I'm so sorry, I have a.
Hey Jeff, very good to see you. At the meeting you didn't attend, they kept referring to you all the time. It was like every time it was like, oh, I wish Jeff was here. He would be able to.
I have interesting things to say about that another time.
Okay.
We'll talk soon.
Next time then. Anyway, thanks for coming.
So I'm majored in biology. So
Oh, right.
I'm not in mathematics or physics.
Sure.
But I'm very interested in quantum computing.
Yes.
Sorry, I missed most of your talk. I come late, but I still have questions.
Yeah.
So, could you explain, like in a simple way, how the quantum computer or quantum computing use the quantum entanglement?
Not in a simple way, but I can like give an idea of how I see it, right? So the idea is that when you have a state vector that's like exponentially long in terms of the number of qubits, and we only have a polynomial size program, then in a way you should think that we cannot get to touch all of these elements in the state vector. There's just not enough time to get it done. The way we get something done is that we entangle these qubits so that when we operate on this qubit, we effectively also operating on this qubit, and actually we're operating on many qubits at the same time. And that's the way we can get